Thus far, we've only encountered aromatic compounds of a particular type, carbocycles, or rings of carbon atoms, with alternating single and double bonds. However, there are other structural motifs that can satisfy Huckel's criteria as well. In this video, we'll consider ions, and in the next, we'll examine heterocycles, which are rings containing at least one heteroatom. It's possible for an ion to possess a continuous cyclic array of parallel p orbitals, in which case it may then be aromatic or anti-aromatic. For instance, consider the cyclopentadienyl cation. This compound is cyclic, and it does indeed have a p orbital on each and every ring atom. To fully understand this, we may need to review our understanding of carbocations. Recall that carbocations are sp2 hybridized, which means that they have one unhybridized p orbital, and it happens to be empty. Furthermore, given the small size of this ring, it must be planar. Therefore, we do have a continuous cyclic array of parallel p orbitals. Furthermore, the cyclopentadienyl cation has only 4 pi electrons, shown in red on the right-hand structure. That's a 4n value, meaning that this ion is anti-aromatic. Another way of visualizing this is through an orbital diagram. The only way for the anion to be delocalized is by placing the lone pair into a p orbital, which allows it to overlap with and therefore be delocalized by the pi system. So essentially, resonance has changed our understanion of hybridization. When we first learned about hybridization, we may have anticipated a carbanion like this to be simply sp3 hybridized. Because that carbon is surrounded by 3 other atoms and a lone pair of electrons, it would therefore hybridize 4 atomic orbitals to accommodate these 4 groups. However, that simplistic view of hybridization neglects to consider the potential for resonance, which may provide an impetus for a different hybridization that would allow great stabilization through delocalization of the electrons. Having shown that there is in fact p orbital character on each and every ring atom, we have established that the cyclopentadienyl anion fits Huckel's first criterion. In other words, it has a continuous cyclic array of parallel p orbitals. This enables us to move on to a consideration of the number of pi electrons in this system. The cyclopentadienyl anion has a total of 6 pi electrons. There are the 4 in the 2 pi bonds, shown in red in the structure, and also we showed through resonance that the lone pair is a part of the pi system as well. So it adds 2 more electrons to the pi system, for a total of 6. This is a 4n plus 2 value, meaning that the cyclopentadienyl anion is an aromatic molecule. One final note about ions and aromaticity. Be very careful not to equate extensive resonance with aromaticity. A case in point is the comparison between the cyclopentadienyl cation and the cyclopentadienyl anion. Notice that they both have 5 resonance structures, which delocalize their charge to each and every position on the ring. Nevertheless, we've shown that the cyclopentadienyl cation is anti-aromatic, while the cyclopentadienyl anion is aromatic. So it's not the number or extent of resonance forms that leads us to one of these conclusions. It's progressing through Huckel's rule, showing that we meet the first criterion in both cases, but that in the case of the cation, there are only 4 pi electrons, a 4n value, making us anti-aromatic. And in the case of the anion, there are 6 pi electrons, a 4n plus 2 value, making us aromatic. The next video in this series will continue our discussion of aromaticity with heterocycles.